Hello and welcome to our lecture on type 1 and type 2 errors. This is something that you might have heard and it's a fairly central and important concept with respect to hypothesis tests. So let's get into what the core concept of type 1 and type 2 errors are. So the idea is the following, right? Take any of the hypothesis tests that you've learned so far. In this course, we've provided you with a template for how the hypothesis tests are conducted. And in this template, you would have noticed the first step is to form a null and an alternate hypothesis. And your last step is that you essentially get a p-value associated with this particular test, and based off of the p-value you either reject the null hypothesis or you fail to reject the null hypothesis. So this is what we have characterized in this table. Okay, so you actually make a null and an alternate hypothesis and you don't know which is true, right? That's why you're doing this test. If you knew, so your null hypothesis was that mu1 equals mu2. So if you knew if that was true, you would not be doing this test. So you don't know if that's true, that's why you're doing this test. So you might have a null hypothesis that says mu1 equals 4.8, which is a single sample case, or you might have a null hypothesis which says that mu1 equals mu2. In either case, you don't know which is true. But let's say there was this all-knowing world where you knew which was true. So that's what's marked out here in actual. You say actually what is true. So here I'm saying the null hypothesis is true, and in this part I'm saying the alternate hypothesis is true. So here I'm saying mu1 is equal to let's say mu2, and here the alternate hypothesis is true. mu1 is not equal to mu2. Okay, now this is the truth. Okay, but based off of some data, right, you did a test. So you might have done a 2-sample z test, or you might have done a 2-sample t test, and let's say that you did the test, you actually computed the z or the t statistic. Based off of the z or the t statistic, you calculated a probability or a p-value, and based off of a p-value you took a decision. And the core idea has always been that if that p-value is too small, then you reject the null hypothesis. And the term too small is a subjective term, and typically people use some line in the sand, some threshold, and that threshold is called alpha. So if the p-value is less than alpha, we reject the null hypothesis. Typically the value of alpha tends to be something like 0.05 or 5%. Okay, so based off of this, let's say you rejected the null hypothesis. That's one decision, and here you fail to reject the null hypothesis for whatever reason. So the idea is that out here you would have rejected the null hypothesis because your p-value would have been less than your alpha. So p value was less than alpha, so you rejected the null hypothesis. Here the opposite was true. P was greater than or equal to alpha. Let's say you don't have to have the equal to sign also. You can just say greater than, and out here you might want to say less than or equal to. Okay, so this is what you did. Now here is the problem, right? If the truth was that the null hypothesis was true, okay, so the null hypothesis was true, which means that mu1 was equal to mu2, right? But you went ahead out here in this quadrant, you went ahead and you rejected the null hypothesis. You said mu1 is not equal to mu2, but in reality mu1 was equal to mu2. You did something wrong, okay, and that error is what is called as the type 1 error. It is when the null hypothesis was true, but you went ahead and you said then I am rejecting the null hypothesis. Okay, and we're going to come back to quantifying that value, which is called the type 1 error. It's just noteworthy that that's also called the producer risk in sometimes, the false positive, or the alpha risk. We won't go into each of those terms. For instance, producer risk is seen more from a manufacturing context, false positives are seen more from a medical context, but if you kind of think about it, it definitely makes sense. Okay, now here is the case out here where the null hypothesis was true and you failed to reject the null hypothesis. So that's okay, you're happy with that, right? Reality was that the null hypothesis was true, and you didn't find any evidence to reject the null hypothesis. So you did the right thing. So you're happy in this quadrant. Now let's come to this quadrant out here. Here, the null hypothesis in reality, because this is truth. So this is truth. So here mu1 was not equal to mu2, and you correctly rejected the null hypothesis. This is still the null hypothesis, right? Your null hypothesis is this. Okay, this mu1 not being equal to mu2 is the alternate hypothesis, but it so happened that the alternate hypothesis was reality, that the null hypothesis was wrong. And when the null hypothesis was wrong, you correctly rejected it. So you did the right thing even here, and that's a very good thing that you did. You actually detected that mu1 was not equal to mu2, and you said, no, I'm rejecting the null hypothesis. So that's a great thing. Now come to the final quadrant. Here the truth was that mu1 was not equal to mu2, but you failed to reject the null hypothesis. You were not able to say, I'm rejecting the idea that mu1 is equal to mu2. I'm rejecting the null hypothesis. You were not able to reject the null hypothesis, whereas you should have, because mu1 is not equal to mu2, and that's the truth. So that's also not a great thing that you did. Okay, and this error is called the type 2 error, and again it's called the consumer risk in the more manufacturing production settings. It's called the false negative in medical settings and a couple of other settings, or the beta risk. Now in really simple words, type 1 error, right, is the concept. So just to be really clear, we're right here. So the idea is that your type 1 error, even before you see any data, right, even before you do anything, could be as high as your alpha. And I say after analysis it's exactly equal to your p-value. So let me explain that a little bit. So let's say you've not collected any data. We just discussed what alpha is. Alpha is this idea that you're going to do this hypothesis test and you're going to get some p-value, and you've already said, right, if the p-value is too low, I'm going to reject the null hypothesis. How low is too low? That's the line in the sand that you draw, and that value is called alpha. So if your p-value is less than alpha, you're going to reject the null hypothesis. What does it mean when your p-value is less than alpha? Okay, first of all, you are going to get a very low p-value. Let's say you're going to get a low p-value, and this p-value is less than alpha, because your type 1 error, first of all, comes about only when your null hypothesis is true and you go ahead and reject the null hypothesis, right? So by definition, that means your p-value must have been less than alpha. Only then you would have rejected your null hypothesis. Now, only when you reject your null hypothesis are you even putting yourself up for the possibility of a type 1 error. Okay, so the idea is that I'm going to tell you that up front, your type 1 error is associated with this idea that you're rejecting the null hypothesis, and you'll reject the null hypothesis when your p-value is less than alpha, which means your p-value is really low. Now let's take a step back and think about what the p-value is. The p-value is this idea that if the null hypothesis is true, this is a definition that we looked at much earlier, even before we discussed type 1 and type 2 errors. P-values by definition express the idea that if your null hypothesis is true, this is the probability of seeing a test statistic as extreme as this, right? If your null hypothesis is actually true. So this probability is really low. Then essentially what you're saying is that you're willing to take the risk and say, the probability of seeing this statistic is just 1% if the null hypothesis is true. If the null hypothesis is true, the probability of seeing something so extreme is just so small, it's just 1%. Then I'm willing to take the risk and reject the null hypothesis. Right? So right there, by definition, the risk that you took was that 1% risk. It was that p-value, right? So whatever your p-value is, essentially if you do the entire calculation and you calculate the p-value, then your p-value is essentially your type 1 error. That's the risk you're taking, that because that is, you've actually calculated the probability that this data could actually occur with the null hypothesis being true. So if you're still going ahead and rejecting the null hypothesis, fully knowing this probability, then that's the risk you're taking of making a wrong decision. Now, of course, before you even see any data and even before you calculate the p-value, given that you set yourself up with an upper threshold of alpha, means that you could get a type 1 error as high as alpha. Okay, so I hope that makes type 1 errors fairly clear. Now, type 2 errors are more complicated. Now, and there's a reason for it. It's a function of a variety of parameters. It's a function of something called delta, which is not the delta that we've discussed so far. And the core concept behind delta is the following, right? Type 2 errors, when do they occur? They occur in the situation where your alternate hypothesis is actually true. So mu1 is not equal to mu2, but you failed to reject the null hypothesis. But in order for me to quantify how likely that is, you need to tell me how much is mu1 not equal to mu2, right? So if I said mu1 is not equal to mu2, okay, because mu1 is equal to mu2 plus a very small number. So let's say 1 micrometer, right? Or whatever it is, whatever the metric of mu1 and mu2 is, but it's a very small number. So mu1, let's say, is 4, but mu2, right, is 4.0000001, right? Then it is true, mu1 is not equal to mu2. The alternate hypothesis is true. But the probability that I am going to reject the null hypothesis just became very low. My ability to discern between a difference, this difference between 4 and 4.0000001 is much lower than my ability to discern between the difference of 4 and 5, all other things being equal. So it's really a function of how different are they, and that's what gets captured in delta. It's also a function of the sample size we take, which is as the sample size becomes infinite, the uncertainty around mu1 and mu2 becomes smaller and smaller, and theoretically even a small difference between 4 and 4.0000001 could potentially be found as long as the sample size is large enough. Okay, it's a function of type 1 error, because your type 1 error tells you how conservative or liberal you're being in rejecting the null hypothesis. So the more conservative you are in type 1 error, meaning that you don't want to make the type 1 error, the more likely you are to make a type 2 error. And similarly, the more liberal you are with the type 1 error, meaning you're okay with some amount of error, the better you're going to be with type 2 error. So it's a little bit of give and take in terms of the type 1 and type 2 error. And essentially a lot of people are very interested in understanding the relationship of beta, which is this type 2 error. Okay, so it's a bad thing, versus delta, which is something we've discussed here, and for a given sample size. And they'll show it for many different sample sizes, and that's known as an OC curve, or an operational characteristic curve. Another word that you might come across is known as the power of the test, and that's equal to 1 minus beta, and it's essentially a very positive thing, right? It's 1 minus a bad thing. So the higher the power of the test, that means the more strength you have in being able to detect a difference between mu1 and mu2. And I've used the concept of mu1 and mu2 coming from the two sample scenarios, but all of these core concepts also apply to single sample tests. Okay, I hope that clarified and that gave you an idea of type 1 and type 2 errors. Thank you.